Hello, my name is Emily Noordyke. I'll be speaking about pollen substitute research today. As you might have guessed, I'm from the United States. I recently moved here to work on the Plan B project with DPI. I'm super excited to start digging in, and I most recently worked for the Bee Informed Partnership, working on commercial honeybee colony health in the US, and then I got my master's degree at the University of Florida studying pollen substitutes specifically with Dr. Jamie Ellis. So I've heard that pollen substitutes aren't as commonly used in Australia as they are in the US, but hopefully you'll still find this presentation useful. So starting with a quick overview so you know what to expect, we'll begin with an introduction on pollen substitutes, then go into a literature review on pollen subs, and talk a little bit about one of the projects that I did for my master's work, and then wrap up with a conclusion. So increasingly, beekeepers are having to mitigate losses in pollen resources. And of course, beekeepers need healthy bees even when pollen is scarce in the environment. And land use change is one of the major drivers of these losses in pollen resources. So increasingly, beekeepers are having to resort to pollen substitute feeding, and that's especially the case in the United States. Pollen substitutes are an alternative source of proteins, vitamins, and fats to natural pollen. And it's important to note that commercially available substitutes do not usually contain natural pollen, although this is changing. There are more and more on the market that do have some fraction of natural pollen, which is great to see. And some common ingredients of pollen subs include soy flour, brewer's yeast, skim milk products, egg, corn gluten, pea protein, potato protein, and this is not an exhaustive list. There are all kinds of different recipes out there, but also note that a lot of the commercially available subs don't include all of the ingredients on their ingredients list because they are proprietary information. And pollen substitutes are used mainly in two different ways. There's the patty form, which is just a moist cake that is placed directly above the brood nest so that the bees can access it within the hive. And then the dry powder form, which is placed in feeders externally from the hive, somewhere in the apiary, so the foragers can go gather that and bring it back to the colonies. So, beekeepers want to know, are pollen substitutes working? Beekeepers want to know if the costs of pollen substitute feeding are justified, and unfortunately, research shows very mixed results. Some studies show a positive impact of pollen substitute feeding on colony health, others still show no impact, a neutral impact of pollen substitute feeding on colony health, and others still show a negative impact of feeding on colony health. So we really should get to the bottom of this. So let's start with the literature review over pollen substitute patties. So we collected a bunch of different peer-reviewed research and tried to kind of figure out the pattern of how pollen substitutes work. So beginning with colony strength, we found that brood production and adult bee population increases with pollen substitute feeding under specific environmental circumstances. One of those including bad weather. So for example, if your bees are experiencing a cold, rainy spring and it's hard for them to forage for natural pollen, then pollen substitute feeding can increase colony strength. However, this study by Matilla and Otis did find that once natural pollen was easily available to the bees again and the weather improved, that it did not have so much of an impact on colony strength, that it was a little bit of a wash. And then, of course, pollen dearth seems like an obvious one. If there's not enough natural pollen available to the bees, then pollen substitutes can increase colony strength. Several studies have found this. But similarly, once that natural pollen flow returned, many of these studies did find that pollen substitutes did not have a significant impact on colony strength. And then finally, pollen substitute feeding during pollen dearth, specifically in Florida, did not result in more brood and adult bees. And because of this study, we wanted to figure out exactly how pollen substitutes were working in Florida, if there was something going on here. So I'll talk a little more about that later with my master's research. And then moving on to the literature specifically on pest and pathogen response to pollen substitute feeding. So we saw a mixture in the literature of this response. In one study, there was an increased prevalence of black queen cell virus in colonies fed pollen substitutes, so that wasn't such a good sign. A few studies showed a mixture of Nosema cerana results. So with pollen substitute feeding, a couple studies showed increased Nosema cerana in the guts of honeybees fed pollen substitutes, usually with particular diets. So not every single diet actually had this effect. And then others still showed no impact of pollen substitute feeding on Nosema. And then a few studies also showed mixed deformed wing virus results. So deformed wing virus is a really bad virus spread around by varroa mites, and they showed that pollen substitute feeding had either no impact or actually decreased deformed wing virus levels in bees. So that could be a positive sign of pollen substitute feeding. And then moving on to the literature specifically on pollen substitutes and how they impact individual bee physiology, so how they develop and how they function individually. Generally, physiological response is positive, but pollen substitutes are often not as good as natural pollen, as you might have guessed. So quite a few studies have found increased hemolymph protein compared to bees that received sugar only. So bees that got the pollen substitutes had more protein in their blood, so that's a good thing. It shows that ingestion happened and the pollen substitutes were actually making some impact. And then others still showed increased hypopharyngeal gland development compared to bees that received sugar only. So the glands of the nurse bees were actually fairly well developed when they were fed pollen substitutes. However, in a lot of those cases, the glands were not nearly as well developed as the bees that were fed natural pollen. So again, that natural pollen seemed to do a better job than the pollen substitutes. Keep in mind that most of these studies were measured in the lab, so it's hard to say whether these things would actually translate into the field with full colonies. But with all of that, the big question here, are honeybees really using pollen substitute patties? And if so, are the pollen substitute patties even effective? So, of course, I'm unable to answer those two big questions just in a couple of years, but they did lead to my first project, tracing the fate of pollen substitute patties in Western honeybee colonies. So basically, we wanted to know, when we put pollen substitute patties in the colonies and they disappear, where are they actually ending up? For all we know, the bees could be ejecting them like debris. And that led to three main research questions. Do adult bees ingest patty? Do adult bees feed patty directly to larvae? And the word directly is important here because the nurse bees will feed a small portion of natural pollen of bee bread directly to the larvae when they are older. But then they also will feed pollen in an indirect manner through the hypopharyngeal glands, through that good brood food secretion. So we were not able to measure that indirect feeding for this project, but we did look at the direct feeding. And then finally, do the bees store patty like they do bee bread for long-term use? So let's dig into some materials and methods here. The first thing I had to figure out was how to trace the patties throughout the colony. So I tested a few different dyes, but figured out that Brilliant Blue FCF, which is just a fancy name for blue food coloring, worked really well for this purpose. It's detectable using spectrophotometry, which is just some equipment that we use to tell whether the dye is present or not. It's generally considered non-toxic, which is great, but I first had to confirm the lack of toxicity to honeybee workers in the lab, and luckily figured out that it was in fact non-toxic and usable. So once we confirmed that the dye was safe to use, I felt good about putting it in full colonies. So thus the field study started. We had 44 links throughout the 5-frame nukes in the study. They were all splits made in March 2019. The study was conducted in May 2019, and we also included 3 sentinel pollen colonies with pollen traps so we could monitor the flow of natural pollen coming in at the same time. And we had 6 different groups in the study, 3 of which were treatment groups, and we used 3 different common commercially available pollen substitutes for this purpose. We used Ultra B, Mega B, and AP23. These are really common in the US, and each of these treatment groups had dye in them. So 7 colonies received Ultra B with dye, 7 Mega B with dye, and 7 AP23 with dye. And then we also had 3 control groups. We had a negative control group that had 9 colonies, and all 3 of those diets were represented in this group. They received the diets without any dye present. And then we also had a consumption control and a positive control, which are a little different, so I'll explain those, kind of break those down in the next coming slides. First, though, I wanted to show you the dyed patty versus the negative control patty. You can see how dark blue-green that dye made the patty, so it was pretty obvious even to the naked eye. So let's talk about the positive control. For this, we decided to use fondant, so this is just a pure sugar patty, and we figured that bees love sugar. You know, everyone knows that. So if we fed them a sugar patty of sorts, they would spread the dye absolutely everywhere. So our positive control shows how the dye moves throughout the colony when we know bees like the diet. So we can then compare that to our pollen substitutes, see how the dye moves when they may or may not like the diet. We'll see. And then the consumption control, which happened to be clay. Jamie wanted me to find a substance that the bees absolutely hated, would not eat, would shred it up and eject it from the hive. And I went to the craft store and collected a bunch of different things, and then figured out that Crayola Model Magic Clay worked really well for this purpose. So it was, slightly pliable, and also the bees would not eat it in the lab, and they also shredded it up, and it would rain down through the screened bottom board, and it just was everywhere underneath the colonies. So it was really obvious they didn't like it. So this consumption control shows how the dye moves throughout the colony when we know bees do not like the diet. So once we had our group set up, we were able to do our feeding and sampling. We used standard mixing methods for all of the different diets to make sure that they were treated the same. We fed those diets ad libitum for 14 days, so they just had diet available to them at all times during 2 weeks. And we closed the colonies early in the morning when we went to sample to make sure that all of the foragers were still in the colonies. We wanted to get a representative sample from the colonies. We then sampled at least 96 workers from the colonies. We wanted to get at least half of those from the outermost frame and half of those from the very middle frame, again to get a representative sample. We then sampled 96 5th instar larvae per colony. 5th instars are the oldest larvae before they pupate and get capped. We just figured that they'd have the most exposure to dye if they were older larvae. And then we also sampled 48 bee bread cells per colony to see if they were storing the stuff. We also collected patty debris underneath the screen bottom boards. So we had trays taped underneath where the patties were placed in the brood nest, and then we were able to collect any debris that fell through. And this example here, this tray in the picture, is of the clay. So that's the dyed clay that they absolutely did not like. So you can tell that they were definitely shredding it up and ejecting it. So once we had all of our samples gathered, we were then able to detect dye in them. So we started with the adult bees. We used something called the UV Vis Nanodrop 2000, which is just a kind of sci-fi sounding name for our dye detector. And We looked at 48 bees per colony using this method. We cut the abdomens off, submerged them in 200 proof ethanol, homogenized, and then centrifuged them, and this was just our way of extracting the dye. And we looked up the absorbance value at 630 nanometers, which is just the spot on the spectrum where you would see a peak if the dye was present. And then we also used visual inspection because we figured out with time that it was really obvious to the naked eye if dye was present. So we looked at the vials and then had somebody either say, yes, dye is present, no, dye is not present, and we did this for 96 bees per colony. And then we detected dye in larvae, and again, it was really obvious if dye was present or not. So we were able to use visual inspection for this. This tray here, these two trays on the left side of the slide, show a negative control. So this was the colonies, these were the colonies that did not receive any dye. They just got the plain diet. And you can see that the larvae have really orange guts, those natural orange guts. Whereas the tray on the bottom is the positive control. So these are the larvae that received fondant. And the dye from the fondant absolutely went everywhere. It was in every single larval gut that we gathered. So that was really cool to have that distinction between our two controls. And then we also detected dye in the bee bread, again using the same methods as we did for the adult bees, and looking at 48 bee bread samples per colony. This picture here shows some bee bread that might look a little blue. This is from the fondant colonies again. So the ones that received sugar, the dyed sugar, they put it everywhere. They actually did cap off their bee bread cells with the dyed fondant. So that was really great to see. So here are the results for adult bee guts. You can see in figure 2, this is the proportion of adult honeybee guts positive for brilliant blue dye when analyzed using spectrophotometry. You can tell that 0 came back positive for dye in the negative control, which was great. And then our consumption control, which was the clay patty, had very, very low positives. And then our positive control, our fondant-fed bees, had the highest proportion of dye in their guts, whereas our pollen substitute groups fell somewhere in between. And this just tells us that the bees were ingesting the pollen substitute to some extent, so just a proportion of them were actually ingesting the stuff. And figure 3 kind of mimics the same pattern, and this was just for the visual inspection of the adult bee guts. So yeah, again, a proportion of the adult bees were in fact ingesting the pollen substitutes. And then moving on to the results for larval guts, we found that a very, very low amount of larvae had dye in their guts in those pollen substitute groups. So compared to the positive control, which had 100% dye present in the larval guts, those pollen substitutes were on the very, very low side. They were mostly statistically comparable to the consumption control. And we think that we got some positives just because some of that patty rains down through the frames and they accidentally end up in the larval cells and can kind of just end up in their guts. So it's more of a false positive, if you will. It's not so much of the larvae actually receiving a lot of the diet from the nurse bees. And then the results for the bee bread. We found again that a pretty high proportion of the fondant ended up in the bee bread stores, and a very low proportion of all of the other groups ended up in the bee bread stores. And we found that some positives happened. They were likely false positives in this case because on the when we were actually analyzing them, the pollen could be a little bit oily, and so that kind of interfered with our readings. It made the spectrum look really kind of irregular. So we had some false positives in our negative control as well as false positives in our patty groups. So from this, we concluded that the bees are not actually storing the pollen substitutes like they are, for example, the sugared fondant. And then finally, the results for the debris. We found that significantly more of the consumption control, or the clay patty, was lost as debris than any of the other groups. So this just shows that they are ejecting the clay, but not so much the pollen substitute patties. So just to rehash these results a little bit, we found that a proportion of adult bees ingested pollen substitute patties of each formulation and also the positive control. Adults do not add pollen substitute patty directly to the larval diets. Adult bees do not store pollen substitute patty like they do bee bread for long-term use. And finally, very little of the pollen substitute patty is lost as debris, unlike those clay patties. So the main takeaway here is that honeybees do not use pollen substitute patties exactly like natural pollen. So if you want to feed patties for long-term provisioning, it probably won't work because the bees aren't storing patties long-term like they do bee bread, and the nurse bees are also not provisioning the larvae exactly the same as they do with natural pollen, so there's a difference there. And then also, it seems that these patties are being ingested by adult bees, but they're really just used in real time. So just some general conclusions. Pollen substitute feeding is a common management strategy, especially in the US. There are mixed results in the current literature that make it difficult for us to determine whether pollen substitutes are effective. And pollen substitutes do not replace natural pollen fully. This is based on the literature review and also the fact that they do not spread the pollen substitutes around the colony the way that they do natural pollen. And hopefully this will inform future developments of pollen substitute feeding strategies as well as pollen substitute research. And I'd just like to acknowledge everyone at the University of Florida Honeybee Lab that helped me with this work, because there was absolutely no way I could have gotten it done without them. So thank you so much for listening today.